Okay, good morning. Welcome to today's lecture. So in the last class, we looked at classification of physical behavior. We said there will be two classes of problems that we would like to categorize. One is equilibrium problems. The other are marching problems, right? The equilibrium problems, we said these are all the steady state solutions of either fluid flow or heat transfer, right, heat conduction. And we also worked with a prototype equation. What was our prototype equation? It was Laplace equation, okay. So it was del square phi equals 0, okay. We also call these type of problems as with a name called elliptic equations, okay. And we noted that these problems require boundary conditions on all the boundaries. So we call these as boundary value problems, okay. Alright, coming to the marching or propagation type of problems. We have again two types. One is we call it as parabolic and the other one we call it as hyperbolic. First let us look at the parabolic type of equations. These are essentially all the transient phenomena, transient or unsteady phenomena. Okay, such as a transient heat conduction or transient or basically unsteady viscous flow, to name a few, okay. So essentially these are unsteady problems that will have a significant amount of diffusion in there, okay. So these are unsteady problems with significant diffusion, okay. For example, if you consider if you consider 1D one dimensional, let's say we have a solid bar, okay, where we keep these two at different temperatures or at the same temperature. Let's say we keep it at T0, which is equal to 0 or something, and then we also insulate the sides of this rod, okay, and we say that the internal heat generation is 0, so essentially everything is 0, but then we start off with some initial profile, okay, for this rod. Essentially we have some initial temperature for the rod, which is T of x at T equals 0 is given with some function f of x, okay. So that means if I draw the initial profile, so this is my x0, this is my xl, and both are maintained at some temperature T0, okay. The initial temperature profile in this rod is essentially given by this function, okay. This is at T equals 0, some function of x, okay. Now what will happen as time progresses? As time progresses, there will be diffusion, right, there will be heat transfer through the ends of the rod and the profile will keep getting diffused, and eventually at T equals, as T tends to infinity, the entire rod will become temperature of T equal T0, okay. So essentially as you can see, there is a significant amount of diffusion with time, okay, the temperature is diffusing down, okay. So these kind of problems are something that belong to a parabolic type of problems, okay. Now a prototype equation for these problems could be the unsteady 1D heat conduction, that is partial T by partial temperature of partial time equals alpha dou square phi by dou x square, okay. So that is a prototype equation. Now, from the equation, can you tell me what all conditions you would need to solve this problem, or what I have already suggested here, right? We would need initial conditions, because you have a transient term t here, and you also need boundary conditions. So, we would need boundary conditions on the boundaries, okay. So, essentially what we need is, we need an initial condition, that is temperature at for the entire domain, that is for all x at t equals 0, right. We would need an initial condition, let us call it some f of x, and then we would need a boundary condition, that is t equals at x equal to 0, we would need a boundary condition, right. And do we need this for all the time or only for the initial time? Only initial time, so that would be t of 0. What do you do at the other times? So, let us say you have a boundary condition of constant temperature, right. You maintain this at t equal t naught. Do you do that for the entire period of the experiment? You would need it, right. Essentially, if you have a Dirichlet kind of boundary condition, then you would need T has to be specified for the temperature on the boundaries, has to be specified at particular x for all the times, right. So, essentially you would need T at x equal to 0 for all the times T, okay. Then we would call it as some temperature T naught, right. You would maintain it as an isothermal condition. Similarly, T at x equals L for all the time, you would need to maintain it as T naught, right, according to what we have discussed in the experiment here, okay. So, the initial condition needs to be specified or the entire domain, whereas the boundary conditions needs to be specified for the entire time, right. Everybody agrees, okay. So, this is simple, alright. Okay, so if we move on, even unsteady viscous flow is an example of a parabolic type of equations, okay. Because of the viscosity, you have significant amount of diffusion happening in the flow, right. Okay, now coming to the hyperbolic problems. These are also unsteady phenomena, these are also unsteady problems, but with negligible amount of diffusion, okay. So, essentially all the analysis or analysis of vibration problems, vibration type of problems dominate this hyperbolic equations, okay. So, if you have a string that is oscillating, or you have a acoustic oscillator, okay, essentially you have a oscillations of a string, or we have an acoustic oscillator, or even if you have a fluid flow at speeds close to the speed of sound. Okay. So, these are close to or more than speed of sound, okay, close to or higher than speed of sound. These are also these are known as what? Supersonic or sonic, right, essentially sonic or supersonic flows. These are also hyperbolic in nature, okay. Now, so for example, if you look at the hypersonic flows or supersonic flows, the viscosity does not play much role in those flows. So, as a result, if you look at the nature of the inviscid flow equations at these speeds, that is, if we define a Mach number that is greater than or equal to 1 at these speeds, okay, these inviscid flow equations behave as hyperbolic equations, okay. So, essentially the viscosity does not play much role in those equations. So, as a result, the diffusion is much lesser, okay. And what we also note is that because of the speeds being very close to the sonic speed or higher, there is a possibility of shock formation, okay, which is a manifestation of the hyperbolic nature of the problems, okay. Essentially, we have because of the shock, there could be some discontinuities that get formed in the interior of the domain, okay. Now, these discontinuities needs to be also captured by your schemes, okay, in the interior of the domain, okay. As a result, it is good to classify the problem before we solve for it, okay, using the particular computational schemes, okay. Now, what will be a prototype equation for hyperbolic equations? Any guesses here? What will be a prototype equation? A wave equation, right? Essentially, if we have a second order wave equation, del square phi by del t square equals sum c square del square phi by del x square, okay. So, this would be a prototype equation which is a second order wave equation, okay, which describes the oscillations of a string, okay. Similarly, you can also have, of course, a first order wave equation, that is dou phi dou t plus sum a times dou phi dou x equals 0, okay. So, this is a first order wave equation. Okay. Now, the kind of schemes we are going to use to solve hypersonic flows or supersonic flows or for hyperbolic equations have to kind of take into account the consideration that there could be discontinuities in the flow field parameters, okay. So, that is something what we need to do before we kind of solve these systems. Of course, for the for the purpose of this course, we are not going to look at supersonic or hyperbolic equations. We are only going to look at elliptic and parabolic type of equations, okay. So, unlike elliptic or parabolic type of equations, which assume the disturbance to propagate immediately in all the directions, right. We have discussed this in the context of elliptic equations. If there is a discontinuity, if there is a jump in the solution somewhere in the domain, that is going to propagate through the entire domain, right, in all directions. We said in the context of elliptic equations, so this is true. So, unlike elliptic and parabolic, in which the disturbance propagates at infinite speed theoretically in all directions, okay. Whereas in hyperbolic equations, the disturbance only propagates in a particular zone, right, only propagates. So, disturbance only propagates in a particular zone, okay. I think this you are aware of. For example, if you have a supersonic flow, you know that there is a zone of influence and zone of silence, right. Essentially, if you look at let us say if there is a source of disturbance here, this can only influence or send signals which are affected only inside this region, which we call it as, let us say, zone of influence, and the pressure fluctuations that are created by this would not be propagating in the other directions, okay. So, they will not propagate in any of these directions, rather they only propagate downstream, right. So, this is a zone of silence when this particular body, if it is moving at a sonic or essentially at supersonic speeds, right. So, as a result, the kind of schemes you would use have to take this into consideration, okay. It is not that the disturbance propagates in all directions, but only in a particular direction, okay. So, that needs to be taken care. What is a good example of this thing? The zone of silence and zone of influence or zone of action. You must have noticed this several times, right. If there is a supersonic flight that is going, by the time you hear it, for example, let us say stand here, right, then by the time you hear it, the jet is already ahead of you, right. Whereas if you have a subsonic flight, one of these commercial flights, then you would see that you would hear the disturbance before the flight is coming onto you, right, before it is approaching, okay. So, as and when this hits you, you are going to get that boom, right, that there is a jet, and then by the time it is already much ahead of you in its direction, okay. So, that is about quickly about the hyperbolic type of equations, okay. Now, we are going to see from a mathematical perspective, I will just come to you, we will see from a mathematical perspective how to kind of classify these equations from a particular classification method, which is going to come next, okay. Yes, at infinite speed, whereas in the hyperbolic or equations, the disturbance only travels at the speed of sound, okay, it only travels at speed of sound. So this is disturbance travels at speed of sound. Well, it travels at speed of sound also in elliptic equation theoretically, but in practice, whereas in theory they can propagate at infinite speed. Okay. Yes. Discontinuities not aware of in solid mechanics, or I mean they could happen in solid mechanics as well. If you have a material discontinuities and things like that, which may kind of give rise to strings, I am not aware of as such. But in heat transfer, I don't think you would get those. It kind of depends on the, you have to kind of make the disturbance or the object that creates disturbance to travel higher than the local speed of sound, right? So whenever that happens, you will get a kind of shock, right? But if you look at, well, it kind of comes back to fluid mechanics again. If you look at the ocean waves, right, you have a shock that kind of gets formed, right? If you go to a beach, you see that there is a toppling of the waves that reaches the shore, right? Essentially, the bottom of the wave kind of catches up with the bottom, and then essentially you get a toppling over. So essentially, at some point, it will be like a shock wave, right? So these happen, but again, it comes to fluid mechanics, okay? But this is in water and as opposed to air we are talking about, okay? Other questions? Okay, then let's move on to, now we have seen that how does the physical behavior happen. We'll also look at a classification method of these partial differential equations, okay? Now, when we say classification, you can of course, so essentially we are looking at classification of partial differential equations. Of course, this is two generic terms, so we are looking at a particular method of classifying them. So of course, you can classify in different ways, right? One classification that you know could be based on linearity, right? You could say a particular PDE is a linear or non-linear, okay? So you can look at linearity and say that I will going to classify equations that I get based on this. What are the other classifications that you know of? Based on the order, right? You can say first order equation, second order, third order. Based on the order, you can classify the equations, right? If you want to just segregate them. Anything else? Of course, what we have just seen, right? Essentially into parabolic, elliptic and hyperbolic depending on the nature of the equations, okay? So we are not going to worry about the first two because we somehow already know that. So we are going to look at the nature that is based on whether it is how the disturbances propagates and things like that. Now, all the equations that we get in fluid flow and heat transfer are second order PDEs, right? So they are only second order PDEs. So we are only going to look at a particular method that kind of classifies a general second order PDE, okay? So we are looking at this particular method of classification which says we look at a general second order partial differential equation and say we would classify them based on certain criteria, okay? Because these equations are the ones we are going to encounter in the entire course, okay? Now, of course, this is not the only method. There, as I suggested, there are several different methods of classifications. This is one particular method for classifying second order PDE or a set of PDEs, okay, that are second order. All right. Now, when I say a general PDE, we are going to now consider a general partial differential equation in x and y, that is in 2 dimensions. So, which I would write it as a times dou square phi by dou x square plus b times dou square phi by dou x dou y plus c times dou square phi by dou y square d times partial phi partial x e times partial phi partial y plus some f phi plus g equals 0, okay. So, let us say this is a general second order PDE that we kind of come across. Of course, the classification method or the type of the equation depends on the highest derivatives of a PDE, Okay. So, as a result we are going to look at the highest derivatives, that is the second order derivatives that we have. So, we are going to look at these second order terms in order to classify this particular equation. Okay. Then what we kind of do here is we are going to look for simple wave-like solutions. Okay. So, essentially if there are simple wave-like solutions that exist for a given equation, then we are going to classify this as a hyperbolic problem. Okay. So, essentially it will be like a hyperbolic equation, and if we are not going to get simple wave-like solutions, then we are going to classify them based on something else as either elliptic or parabolic. Okay. Now, what has gone in behind this thing which we are not discussing is basically whenever you have a hyperbolic equation, then there could be discontinuities across the, let us say for example, shock waves, right. So, essentially these shock waves, if we consider them as characteristics, there could be discontinuities across these characteristics. Okay. Now, that is what we are invoking, okay, assuming that the there could be, so essentially there could be second derivatives could be discontinuous across something that is known as characteristics. Okay. Now, these characteristics could be thought of as the shock waves. Okay. Now, we kind of invoke this as well as the continuity of the first derivatives, and we come up with a characteristic equation. Okay. So, if we have a characteristic equation that I can construct from this second order PDE, and if that characteristic equation has two real roots, then I can say that I have wave-like solutions coming up from my PDE. Okay. That is something which I am not discussing here, but you would take it granted here in terms of the equation. So, essentially if we look at a characteristic equation for the second order PDE that we wrote above, that would be A times dy by dx whole square minus b times dy by dx plus c equals 0. Okay. So, where dy dx is the kind of gives you the slope of the characteristics. Okay. Now, this is a characteristic equation. If this equation has real roots, then we are going to say that what I am going to get is a hyperbolic equation, because that will have two real characteristics through which the information propagates. Okay. Now, all this is kind of has started, the classification of these things has started because if you can find these characteristics, you can actually reduce your PDE to an ODE along these characteristic lines. Okay. And then being an ODE, you can solve it in a much simpler way than a PDE. That is how all these methods have kind of originated. Okay. That is why we are giving so much emphasis on the characteristics and the wave-like solutions and so on. Okay. But we are not discussing that as part of this course, okay, as part of the CFD course. But if you have taken some course in gas dynamics or something, you would be taught some of these characteristics and reducing the equations along the characteristics and solving for them. Okay. So, which we are not doing it here, but this is known as method of characteristics, which you can look up, and which reduces the PDE to ODEs along these characteristics. Okay. All right. Now, we take it for granted that there is a characteristic equation that we can write for the given PDE, and that is A times dy dx square minus b times dy dx plus c, where A, B, C are what? They are coming from they are the same values as the coefficients that we have for here. Okay. Those are the same values. Now, here what I assume is that I assume that for this PDE, A, B all the way to G are all constants. Okay. I am assuming that these are all constant. As a result, what will be the type of this equation? Is it linear or non-linear? Linear, because they are all constants. This will be a linear second order PDE. Now, what would make it a non-linear PDE? What should I set A to Z as, or at least A to F as? Either function of No, if they are function of x, y, is it nonlinear? It is still it is still linear, right? Because x, y are known, right? So it is still, it should be either function of phi or its derivatives, right? It should be either function of phi or its derivatives, then it will be a nonlinear PDE, right? Of course, you are right in some sense. If they were functions of x, y, if my equation was not a PDE, if it was an algebraic equation, it will be a nonlinear algebraic equation, right? If I have something like y square plus 2xy equals 0 or something, then because there is a y multiplying y, that's a nonlinear equation, but this is a nonlinear algebraic equation, right? But in the context of ODEs or PDEs, the coefficients have to be either functions of phi. Essentially, they should be functions of the dependent variable or its derivatives, not the functions of independent variables, right? If they are functions of independent variables, that is still a linear PDE or ODE, right? Okay. Alright, so we initially assume that these are A to Z are all constants. However, this method works even if they are not constants, okay? This method of characteristics and things like that, which we will kind of briefly discuss. Okay, now now this equation to have two real characteristics, essentially the b square minus 4ac is what I have to look for, right? Has to be, if it is, when will this equation have two real roots? When this is greater than 0, you would have two real roots, okay, which would make the equation as what? Hyperbolic, okay. Now, if you have b square minus 4ac as equal to 0, how many roots we would have? We have only one real root, and that would make this equations as, we should make it as parabolic. Okay. Similarly, if you have it is less than 0, you would not have no real roots. That means we don't have real characteristics, you only have like imaginary characteristics. So this we call this as a elliptic type of problem, okay. Now, well, I have been discussing this parabolic, hyperbolic, elliptic, all these things for now couple of lectures. How does these come about? Why do we call them hyperbolic? Why not some other name? It's essentially because of this b square minus 4ac is what we are using to kind of classify them, okay. This kind of resembles to the conic sections that you might have learned, right, where if you have these greater than 0, you're going to get a hyperbola, if it is equal to 0, you're going to get an ellipse and so on. So this essentially stems from the conic sections theory, and other than that there is no other resemblance between the hyperbolic and all these things, okay. So that's one thing which you have to keep in mind. Okay, so far so good. So now we have kind of found an equation using which we can classify the second order PDE that we have, okay. Now we say that this method still applies if you have A to F functions of either phi or its derivatives, okay. Now what does that mean? The moment you have these coefficients functions of phi, partial x, or if they are functions of x, y and so on, what will happen to the type of the equation? The type of the equation may change from point to point, right, in the domain, because now these are functions of x, y, the relative values of a, b, c could change. As a result, the value of b square minus 4ac could change from location to location because of this thing, right. So that means when we talk about a particular PDE, depending on the coefficients, the type of the PDE could change, okay. So that's what I kind of want to emphasize here. For example, let's look at an example problem. Essentially, example 1. We take the equation which is Laplace equation, partial square phi by partial x square, partial square phi by partial y square equals some function, or we look at the Poisson equation, some function of x, y, okay. Can you tell me what is b square minus 4ac here? Or to begin with, what is a? A would be 1 because that is the coefficient here. What would be b? B is 0 because you don't have a term of mixed derivative, right? Partial square phi by partial x partial y is not there, so b equals 0. What would be c? C is 1, so what is b square minus 4ac? Minus 4, okay, this is less than 0. So that's why this equation is elliptic, okay. That kind of satisfies what we earlier discussed in the context of elliptic equations. Okay, let's look at another example. If we take the unsteady heat conduction, okay, so that is partial phi by partial t minus alpha partial phi by partial x square equals 0, okay. Now what is A, B, C in this? A is minus alpha, B is 0 because you do not have mixed derivative, right. We do not have dou square phi dou x dou y or dou square phi dou x dou t, none of them are there. What about C? C is also 0. So what is B square minus 4AC here? 0. So is this, does it qualify as what type? Parabolic, like what we have written, right. So this is 0. So this would come out to be parabolic type parabolic, right. So this is a parabolic equation like what we discussed before, all the transient equations with negligible, with significant amounts of diffusion, okay. Now let's look at another example. Of course, the only thing remaining is the hyperbolic. So what is the equation we have for hyperbolic? This was second order derivative was partial square phi partial t square minus c square partial square phi partial x square equals 0, right. That is what I wrote. Now what is A, B, C here? What are the independent parameters that independent quantities here? X, not x and y like what we had before. Here it is x and t, okay. So what is A, B, C? A is minus c square, okay. B 0 because we do not have mixed derivative. C is 1. So what would be B square minus 4AC? 4c square, okay. So this is greater than 0. So this is hyperbolic, okay. We can of course keep doing this for several problems, fine. Okay, now let us look at, so all these till now all the three equations we have seen have A, B, C as constants, right. Now let us have another problem where the coefficient is not a constant but it is dependent on example 4, but it is dependent on one of the coordinate directions. For example, I will take y dou square phi by dou x square plus dou square phi by dou y square equals 0, okay. So we want to know what is the type of this equation in the over the range minus 1 less than or equals 1, y less than or equals 1, okay. In the range minus 1 to 1, we want to know what is the type of this equation, because earlier the type of the equation is the same everywhere in the domain that you consider irrespective of the domain extent, okay. Now what is A here? Y, B is 0, C is 1. So what would be B square minus 4AC? Minus 4y, right, minus 4y. Now is this greater than 0 or less than 0? That depends on the value of the y of course, okay. So if y is less than 0, right, so essentially y is less than 0, then this would be B square minus 4AC is greater than 0, so this will be what? Hyperbolic. If y equals 0, of course B square minus 4AC would be also 0, this would be parabolic. And if y is greater than 0, the discriminant will be less than 0 and this will be elliptic, okay. Fine. So essentially the equation now we have written here is a mixed type of equation, right, whose is a mixed type of equation which whose type depends on the region that you are looking at, fine, okay. Now you may have a question here, okay, you just told us that depending on the method we would choose a particular, depending on the type of the equation we would choose a particular scheme or a type of method. Like what do you do now if you have an equation like this? These are very tough to solve, okay. If you have an equation where you are going from, let's say, parabolic to elliptic to hyperbolic in one solution domain, these are very difficult to solve numerically, okay. That means what we are looking at, we are looking at a simple domain where you have a subsonic flow followed by some kind of transonic flow and then supersonic flow all happening in like one region. Those are really tough problems, okay. Probably you cannot do it with one solver, so you have to make some compromises and things like that, okay. Any other questions? Yes. First order wave equation, very good. Okay, I'll come to that now. So, okay, another example is partial phi by partial t plus c times partial phi by partial x equals 0, right. So, this is a wave equation of first order. I said this is hyperbolic. Now, how do we prove that this is hyperbolic? Okay, of course, one caveat I said before was we are looking at classification of second order PDEs only. So, I did not look at the first order PDEs as such, but of course, you can convert this to a second order PDE by just differentiating with respect to x or t, right. I would just differentiate with respect to x. So, this would be partial phi by partial x partial t plus c, assuming that c is constant, this would be partial phi by partial x square equals 0, okay. Now, what is a, b, c here? A equals 0, b equals 1, right. A equal to c, okay fine, let us call with a different name. I think we have two c's here conflicting. Let us call this as plus some velocity, let us call it w, okay, w. So, what would be a? Okay, a you want to call it as w, right, because we said this term is the first term, okay, is that correct? And then b equals 1, c equals 0. What would be b square minus 4ac? 4ac is 1, which is greater than 0. Is this, what type of this equation is? Hyperbolic, okay. Now, of course, you do not have to stop here. A follow up question would be, now how do I convert this equation to a second order wave equation, right. So, here I have differentiated with respect to x, you differentiate with respect to time. What you are going to get is partial square phi partial t square plus w partial square phi by partial x partial t equals 0, right. Now, you could form a second order equation from these two terms, right, which is same as before, okay. So, you kind of get rid of the mixed derivative from these equations and you can end up with an equation which is in terms of a second order wave equation, okay. Now, in general this method will not apply if you have anything other than second order PDEs, okay. Other questions? I am expecting a lot of questions here, okay. If you do not have questions, I will ask your questions and answer them. Yes. Yeah. Along the characteristic lines, yes, yeah. Yeah. There will be two characteristics, yes. You would solve along both of them. Right, essentially you would solve along both the characteristics. Let us say one on the top, one on the bottom. Yes, which goes as a plus and a minus, and then you would draw along both of them. You would kind of solve along both of them, okay. Yes, exactly. Of three variables, yes. So, essentially the question is, we assumed of course that phi is a function of only x, y. What will happen if phi is a function of x, y, z or something else, right. So, but still the PDE we are looking at is a second order PDE, okay. We are not going more than that, okay. That is fine, because let us say you want to solve in a 3-dimensional domain the Navier-Stokes equations which are second order, but the domain is now 3D, right. I have x, y, z. Of course, what we discussed does not work, okay, but a logical extension of this will work, and that would be our next discussion. That is essentially if you have, let us say x1, x2 and so on, xn, these are the independent variables that we have, and we are looking at a general second order PDE that is in n dimensions, okay. Then what you are going to do is, the treatment is similar, but then the way we classify them is slightly different, but which brings in the same kind of concepts, okay. So, I am going to kind of not derive it, rather write the solution here. So, if we have an equation like this, then what would happen if we go back, what will happen to our general PDE? It is here. So, you are going to get more terms, right. What terms do you get more? You of course get some h times dou square phi by dou z square, right, plus you would get mixed terms in terms of xz and so on, right. So, it will be gigantic, we are not going to write it, okay. So, what we write it is, we would write it in a nice compact form, okay. So, we have, we can write that as a, essentially we are going to get terms which are multiplied with dou square phi by dou x I dou x j, okay, where xi, xj could be either 1, 1, 1, 2 and so on. So, this could be xx, xy, yz and so on. Each of them will have some coefficient. All those coefficients, I am going to write it as sum aij, okay, that is kind of a matrix, okay. We have all these terms in there, plus we have lot of terms which are not second order derivatives, okay. Let us call it sum b, okay. So, these are all the first order terms and the constants and so on, okay. And all these have to be summed up on what? I equals 1 to capital N, j equals 1 to capital N, right, e equals 0. So, this is our now second order PDE in n dimensions, right. If you plug in n equals 3, you are going to get for x, y, z, okay. Now, what do we do for this? Of course, it is kind of a logical extension of what we discussed. The answer to this lies in solving for or in solving and looking at the eigenvalues, okay. The eigenvalues of this particular coefficient matrix Aij, which is similar to what we have done in the context of just two coordinates, okay. So, we have to construct Aij minus lambda I, construct a characteristic equation like this equals 0, look at the eigenvalues that you get here, okay, these lambdas. Now, depending on the value of lambdas, you are going to classify the equation, okay. This is something I am going to give you as a recipe without proof. So, if you have, if there is any lambda that is equal to 0, then we are going to call this system of equations as elliptic, okay. What do we have here? We had similar one, equal to 0 was parabolic, right. This is parabolic, okay. So, if we have any lambda equal to 0, we are going to call it as a parabolic type of equation. If all the lambdas are not equal to 0, but are of the same sign, okay, then we are going to call it as a elliptic type of problem. Again, all the lambdas are not equal to 0, but all but one are of the same sign, okay, then we are going to call it as hyperbolic type of equation. Now, this is you would need this, right, if you want to classify the Navier-Stokes equations in 3 dimensions, okay. Now, of course, again depending on these Aij values, the classification we are looking at could depend on region to region, okay, that could also be possible. Other questions? Yes. So, say it again, sorry. Yeah, all but one of the same sign. For example, if you have looking at 3 dimensional, so the question is all but one are of the same sign in 3 dimensions. So, if we have 3, for example, the lambdas could be 2 of them positive, 1 of them negative and things like that. So, one eigenvalue has to be of different sign than the other 2. Yeah, it's kind of, so it will be the same conditions even if we have n dimensions. So, the question is then what will happen, what will be the type of the equation if this is not satisfied, is it? So, but then you would end up with some zeros in the lambdas. You would not have a condition where more than one lambda is of the same sign, okay, in the classification. One thing is, it is very difficult to look at more than 3 dimensions in this. Of course, you can involve time as another dimension, okay, as a 4th dimension, but we do not have another classification method here. So, I guess if you end up with something, probably that will again fall into a hyperbolic type of equation depending on the method, okay. Other questions? Yeah, I mean there are several things that may come up, but I think they all belong to the hyperbolic thing, okay. You do not have the conditions on the parabolic and elliptic are clear in terms of if you have a 0, then that is parabolic. You could have multiple zeros also, that will be in the parabolic, but if they are all the same sign, that will be elliptic, and if you have all, let us say, mixed type of lambdas, then you end up with hyperbolic. But these will be very difficult to get in practice. We probably may have like a toy problem that may show these kind of things, But in practice, very difficult to have a physical problem that will give anything else than what is kind of displayed here. Yeah. In general equation, oh, in this equation itself. In this equation itself. Yeah, so there will be, of course, there will be terms with, so all those terms which are, so the question is, there will be more terms which are partial phi, partial x, right? They are all absorbed into B, okay, because we are only looking at the highest derivatives to classify this equation, okay. So B is not a constant but contains the constants plus all the first order derivatives, partial phi, partial xi, okay. Other questions? Okay, if you have a nonlinear equation, so Aij is a phi or partial phi, partial x, right? So then the current iterate value of that phi or partial phi, partial x has to be used. For example, you are solving for it, you have to give some value for the phi. So essentially, the nature of the equation will change as you progress your solution, right? Because it's nonlinear. So it's like the type of the equation will not be known until you get a solution, or it will keep changing as you progress the solution, right? Because we are trying to solve for phi, and if phi comes as a coefficient here, we would not be able to tell the type, okay? But those are also very hard to get unless you have, well, some equations are there which will kind of belong to the hyperbolic family, for example, Burgers equation and things like that, where you have the coefficient is multiplied with a u, where the unknown is also u, okay? Other questions? Now, okay, one important question is what is the type of the Navier-Stokes equations? Let's say if you have, right, that would be your next question. So Navier-Stokes equations, you can show that the incompressible flow equations are of parabolic elliptic type, okay. So it's kind of a mixed thing. So you can show that the Navier-Stokes, the incompressible equations are of parabolic elliptic type. So I think, so what I mean is elliptic parabolic is basically the pressure terms behave like elliptic equations and the velocity terms behave like parabolic, okay, because now you have extra variable pressure, right, you have velocity as well as pressure, unlike these equations we have written, right, here the only variable is phi, right, but in Navier-Stokes you have pressure and this one, and if you go to compressible Navier-Stokes equations, this behaves more like parabolic hyperbolic, okay. So this has a lot of consequences in designing the numerical schemes for the solution of them, okay. So this has implications in the design of numerical schemes for solving these type of problems, okay. I think the takeaway message is if you have elliptic kind of problems, the schemes you would use would be kind of sending the information in all directions, whereas if you have hyperbolic, then you have to be careful in terms of how you gather the information, okay. Especially if you have a shock and things like that, you have the numerical schemes have to be kind of careful enough that they don't pick up the data from all the sides, okay. So these are very important. Other questions? Okay, I have one question. So why not just write compressible flow equations and develop a solver for that and then run it for incompressible flow, right? Why do we care? We will just write for a compressible flow solver and make it work for incompressible also. Would that be fine? Because I just said that, okay, it will be very difficult to solve for incompressible, compressible or a range of Mach numbers and things like that. Can we do that? Oh, no, we cannot do. So we cannot just work with a compressible flow solver at incompressible speeds, right? As an incompressible situation. Why? Sorry? So essentially the nature of the equations would change. As a result, the things you are trying to solve would kind of degenerate, and you would end up with kind of a stiff equations, okay. So the same problems that you would encounter in directly working with incompressible flow equations is what you would encounter if you try to solve from a compressible perspective as well, okay. So in the limit of, let's say if you have a compressible solver, you try to run it at speeds at a much lower speeds. Let's say for example Mach numbers less than 0.3 and 0.2, then you would encounter the same kind of problems as you would encounter in if you start off from an incompressible flow equations, okay, for which we have some remedies, okay. So, right. You usually will have a lot of difficulties in converging the solver. So, there could be some special treatments which you have to borrow from the concepts of incompressible flow solutions to be put into the compressible thing, okay. In which case you can actually probably just be well off solving the incompressible flow equations rather than the compressible ones, because the speeds are so small that there are no density variations. The density is less than 5% or 3%. Okay. All right. Then I'm going to stop here. In the next class, so this kind of finishes the chapter 1, that is the review of the governing equations, looking at the general scalar transport equation. So we have chapter 2 coming up in the next class, that is overview of numerical methods. That is also a kind of very short chapter. We will try to finish it sometime over the next week. Okay, thank you.